Sorry for the delay. Now, so we're going to continue with radicals. So we looked at, who remembers from last time, 6-1. What was the gist of 6-1? What was the main component that we talked about with radicals?
If it's squared, it can't be a negative number. If it's cubed, it can't be negative. So if it's odd, even,
Good. The index being odd and even. Very good, Nick. And we talked about imaginary numbers. And those came about when there was a negative underneath the square root. Okay, that's where the imaginary numbers came from. So keep that in mind. All right? Now, today what we're going to do is we're going to look at the properties of radicals, some of which you probably know already, and others of them that might be new to you. Okay? So I might go through some a little quicker than others, but let's just think about what's going on here. So let's take a look at the first example. Well, let's write down our properties. Sorry, I should point those out first. What does this first property tell me? Can somebody describe in words what this property means up here? How would you describe it? What is it actually saying to you? Radical AB equals radical A times radical B.
I had a good thing to say. AB is the same. It's like you're squaring them each individually.
Good. It's like you're taking the square root of them individually. Very good. So if you have two factors under a radical, you could take the square root of them individually, which really tells us that we can break up the number under the radical. Okay? And the second part, Nick, continue, since you got the first part, I assume you know?
I can't see that on my glasses.
So it's radical A over B equals radical A over radical B.
Equal? Is there a difference between each one?
Well, the first property, what operation is this right here?
Multiply.
And this operation is?
Division.
Yeah. So division holds true as well. So if you have the division of two numbers, so like say you have radical 9 over radical 2, or sorry, radical 9 over 2, you can break it into radical 9 over radical 2. So we're just thinking about separations, okay? So the first one, radical 75. I can break 75 up into many numbers, okay? I mean, I could break them up into non-integer values. I could say, well, you know what? And I'm not going to do this because this doesn't really make much sense, but I could say that this is really the square root of 37.5 times the square root of 2, because that gives me 75. But that doesn't really help me much, right? We all agree? 37.5 times 2, that is 75. But those don't really make this any easier. So those might not be numbers I would want to choose. Mike, what do you think you might want to choose here? What numbers go into 75 that might make this problem a little bit easier for me? Yeah. What are some of the factors of 75? Yeah, 25 and 3, good. So let's write that like this. 25 under the radical times 3 under the radical. Well, Mike, why does this make it easier? What's the square root of 25? It's just 5. So this just becomes 5 times the square root of 3. And that's the simplification of the square root of 75. So what's the goal here? Somebody tell me what the goal is. What did we try to do in this problem? Manny?
To split up the problem.
Into?
Into two of them.
Two of them, one of which is?
A perfect square.
Perfect. That's exactly right. So if you want to write that down, you should. The goal is to break up, again, break up the radicand into two new radicands. So again, break up the radicand into two new radicands, one of which is a perfect square, or where one of which is a perfect square, or perfect cube, or perfect fourth, as we're going to see in example C in a minute. Okay? So again, we want to break this up into two other radicands. Here they are. Here's one radicand, here's the other, one of which is a perfect square or cube or whatever it is that we're looking for, so that we can then reduce it. Now, here's a little suggestion, and you don't have to do this, but I always do it. I put the perfect square first, so that it reminds me to, when I break it down, to put the integer value now on the outside. Okay? It is not traditionally done where you see radical 3 times 5. Okay? Always put the numerical or the integer value on the outside as a coefficient. Is that clear? As a coefficient. All right, the second example. The second example. At first, it seems as if there's not much we can do. I can break up 8 into 4 and 2, but that 6 is still bothering me. So, what do I get if I multiply 8 times 6? Everybody?
48.
Thank you, Mahanor. 48. So I have the negative of radical 48. Now, before we go any further, Katarina, is this imaginary?
No,
Why?
because the negative is outside.
Very good. That's a common mistake that people made on the midterm and on the last exam. If the negative's on the outside, it's just saying the negative of whatever this quantity is. Therefore, here, we actually can break this up. What is a perfect square that goes into 48? And you want to find the largest perfect square now. Because 4 definitely works. Right? 4 times 12 is 48. But then you can break up the 12 into 4 times 3. So clearly it's not the best answer. What number goes into 48 that's a perfect square that's bigger than 4? 16 and 3. Very good. So put the negative on the outside. It doesn't matter where it goes. And let's write this as 16 times 3 now. Do you see what's happened? We've gone from 8 times 6 to 16 times 3. So what we did, we multiplied and then we factored, which seems counterproductive because we're like doing the opposites, right? Why would you multiply and then break it into factors? Well, because now we have a perfect square here. What's the square root of 16? 4. So I'll just write this as negative 4 root 3. Okay? So again, what do? We saw that this could be broken up, and this could be broken into 4 and 2, but when you have two things multiplied, try multiplying them first, and see if you can take out a larger perfect square. Let me write a little side note down here, okay? It's for something for you guys to see. If I had done it another way, let's say I had done this, and broken it into... Oh, I should put a negative out here. Say I've broken into 4 and 12, because 4 is definitely a perfect square, right? It looks like this would become 2 radical 12. But what's the problem with 12? Is 12 broken down fully? What can 12 be broken into that's got a perfect square in it? 3 and 4. So this is really this. And then the 12 becomes, right? That's what 12 is. So really, take a look. What's 4 times 4, everybody? Which is this quantity here that we had before. Okay? So again, if you don't break it down fully, you're going to have a component that's left that can be then broken down more. So if we didn't break this down correctly, this 12 gets then reduced to 4 and 3. Okay? Gets reduced to 4 and 3. Which, again, these two end up becoming the same thing as what we had up there. And the radical 3 is right there. Okay? Let's look at part C. Let's take a look at part C. Now, what do you notice here? What's the difference between part C and part A and B? What's the difference, Peter, in part C as opposed to parts A and B?
They're exponents.
Yeah, not exponents. What's the other word, though? Because the exponent's when it goes out here, right? When it's raised to a power.
I don't know.
Anybody want to help me out with that word? Index. But you understood it, but just use the right terms. So index there, index. So write that word down if you didn't know it, please. Index. So the index is no longer 2. The index is 3. So perfect squares aren't going to help me at all this time. It's not going to be useful to look at numbers like 36 and 64 and 81. Those are not useful anymore. I want to look at perfect cubes now. Remember when we listed the perfect cubes that day? We listed them on the side. And in case you don't remember, we did this. And I told you to stop at 5. I said you could know 6, but at least know up to 5, okay? These are the ones that we talked about. So, let's take a look. What can 25 be broken into? There's just really pretty much one thing that can be broken into that are integer values. 5 and 5. How about 10? 2 and 5. Are 5 or 2 or 5 perfect cubes? They're not. So that's not useful, right? It's not worthwhile to break it down. So what can I do to the two radicands maybe to make it easier? Yeah, what do I get, Nick, when I multiply?
250.
Yeah, very good. Please, Erickson, tell me, out of these perfect cubes here, look at the right side, okay? Which of those perfect cubes goes into 250? Yeah, 125. Very good, right? It's like $2.50 and $1.25. How many times does it go into 250? Yeah. So wouldn't you just do this, right? Again, let's take a look. We start by looking at the radicand and say we are looking at a cube root now. So we want to figure out which perfect cube goes into the radicand. Well, 1 does, but again, 1 never helps me. 8 does not. How do you know 8 doesn't go into 250? Anybody know how 8 doesn't go into 250? 8 times 3 is 240, right? So 8 times 30 gives me 240, leaving behind 10. 10 is not divisible by 8 evenly. You'll get 1 remainder 2. So you can tell right away. You can try them in your calculator. You can say, right, let's try. 250 divided by 27 doesn't come out to give me a whole number answer. 250 divided by 64 won't come out to give you a whole number answer. But 250 divided by 125 surely does come out to give you a whole number answer. Now, what's the cube root of 125? It's just 5. How do you know that? It's written on the board. Very good, Manny. Right here we look. We see 5 cubed is 125. So the cube root of 125 is just 5. So replace that with the number 5, please. And then leave behind the cube root of 2. Please make sure your penmanship needs to be immaculate. It really does. You know why? Because this little 3 here, a lot of you are writing it really large. And to me, it would be 5 times 3, root 2. Okay? This is what I'm seeing sometimes. That's not the same thing. Okay, the 3 needs to be above this little piece of the radical right here. It needs to be above it, and it needs to be written small. This could be interpreted as 5 times 3, radical 2. Is that clear? Again, and those of you know who you are. Radical 120 over radical 10. Okay. I could start by trying to reduce both of these, right? Try to break up 120 and break up 10 and not find perfect squares to make them smaller. But I could also go ahead and look back at my rule, and my rule told us that if you have two things separated as radicals, you can put them together, or if you have them together as a quotient, you can separate them. So we have them separated, right? So let's write them together. If I wrote these together, it would look like this. What's 120 over 10, Johnny? 12. Yeah, so that's easy. Isn't it much easier now? And now, John, tell me, what can 12 be broken into? 3 and 4. Well done. And why did I put the 4 first? Because the 4 is the perfect square. Okay? Square root of 4, everybody. Louder, I didn't hear you. Thank you. Okay? 2 radical 3. So far, so good? So, what have we covered just now? We covered multiplication of radical expressions and division of radical expressions. Now, the next thing we're going to learn, okay, are simplifications when we have variables involved as well, not just numbers anymore. Okay, variables involved as well. This is no more difficult than what we just did. Okay, it looks different, but it's the same process. So when you're doing your homework, you need to think to yourself, this is the same as if there are numbers. I'm still breaking it up, but it just looks different. Okay, it looks different. So if I want to figure out the square root of 3ab squared, okay, 3ab squared. Now, first of all, break it up into its components in your mind. Here's what I'm thinking about. You don't have to write this exactly, but here's what I think. Okay? Why can I do that? Because these are all what? What's the term? They're all what? Not prime. Louder? Factors, right? Factors. Again, if you go back to your rule, the rule that we stated a minute ago, okay, the rule that we stated was that if you have the square root of AB, you can break it into the square root of A, then the square root of B, because they were factors, they were multipliers. They're not addends, okay? So in this last example down here, are we going to be able to break this up for part D? No, those are addends. We can't break it up. We'll talk about what to do there. Now, let's go back. So, can you break up the square root of 3 into anything? Yeah, does 3 times 1 help me though? Good. What about the square root of a? Can that be broken into anything? There's nothing you can break. 1 times a, but that's pointless, right? But here, what's the square root of b squared? It's just b. Why is that? Erickson, why is the square root of b squared just b?
Because it's b times b.
Yeah. And when you look for a square root, you're looking for something times itself, right? Like the square root of 25 works because it's 5 times 5. Just like here, the square root of b squared is just b times b. So the square root of b squared is b. And then the a and the 3 can't be broken down. So let's put them back together. And let's write this in our traditional form. Okay? Again, break up whatever you can. Whatever you can't break up, just leave it under the radical. It's not going to hurt you. It's not going to do anything. It's just the fact that it's still under the radical. Okay? It's still under the radical. Now, let's take a look at example B here. (49y to the 5th). Suggestions, Johnny?
Is it 7? You can read y 2.5.
You're on the right track, and that's what I like to hear. You said 7y to the 2.5 because you took the 5 and divided by the 2, which is the index, like we did. Very good. But we don't want decimal values as exponents. So, what we want to think is, can we break up y to the 5th into something with an even exponent and something with an odd?
2 and 3. 4 and 1.
4 and 1. Yeah, 2 and 3, there's an even and there's an odd, but the odd can be broken further. So, think about this as the following.
49 just squared.
Okay? Again, Johnny started by saying, well, y to the 5th becomes y to the 2.5, which is totally true. But if we're looking for whole number exponents, which we are, we want to think about break up this into something that has an even exponent. Because the index, what's the index here really? Everybody, what's the index? Ooh. What is it? Peter? Good, thank you. Very good, Pete. 2. The index is 2. And if you remember the rule we came up with, okay, the generalization that we made was that we can take the exponent here and divide it by the index to reduce it. Well, this exponent was 5, wasn't it? 5 is not divisible by this 2 that's out here. So it didn't work. So Johnny recommended at first 3 and 2. And the 2 can be broken down, but the 3 can be broken even further into 2 and 1. So let's find out the even number that is less than this number, but as big as possible. Okay? Again, this could have been 2, and this could have been 3, but then the y to the 3rd would be broken down even further. Okay? What's 4 and 1?
5.
This 4 and this 1 becomes 5 here. So we're breaking them out separately now. So let's reduce it. 49 becomes y to the 4th as a square root becomes y to the 2nd. Again, remember, there's really an imaginary 2 as an index in all these spots. This rule that we came up with, the conjecture that we made, was that we could take this exponent and divide it by the index, provided it divides evenly. Okay? So we have 7y squared that reduced. What's the square root of y? The square root of y is not y.
Is it? No, I got 1.5 y or something.
Oh, I guess you're saying point y to the 0.5, but again, we can't have decimal exponents, right?
Would it be 1 to the y? 1 times y?
No. What, Jules? It stays. You're not going to break it down. Okay? Again, the square root of y is the square root of y. There's nowhere to go there. Okay? There's nowhere to go. And please notice, see this 2 here? This 2 is not an index. It's not sitting over this little piece. It's sitting up here as an exponent for this y. So this is 7y squared times the square root of y. Is that clear? How can you tell the difference? I mean, I would write it like this if it were the other way. Does that look different to you or no? Really? Those don't look different? Okay, so clearly they don't look different. Let's see.
Can you just like put a dot in between?
Put a smiley face.
Sure, you can do that if you want. Here. You can put a dot there, and then in this case, put a dot there to show it. That works. Okay. You can just emphasize like this. Watch. Write this the following. Is that different? Is that obvious now? Okay. So we'll make sure to emphasize that. Yeah, just really emphasize it then. These two things again. This is 7y squared, square root of y. This is 7y. But would you ever put a 2 as an index? It's already there. So that really should never affect you just for the 2. But the next part might with a 3 as an index. Okay? But again, you're never going to write a 2 as an index. Okay, people? Part C. What do I do when it's division? Alejandra. Good. Okay, so again, we start by separating. Y and W are two different variables. Don't think of them together. Break it apart. Okay, break it apart. Now, Johnny, I want you to answer this question because you got the last one, but it's a follow-up. Now we have a 3 as an index. So what does the denominator become automatically? Good. Or y to the 1, right? But the numerator we can't do, right? Can 4 be divided by 3, everybody? Evenly? No. So what do you break the numerator into now?
1.
Good. Is that clear so far? The denominator was easy to reduce. Reduce the denominator right away. How come we can reduce the denominator? Because 3 divided by 3 is just 1. So that's done. But the numerator cannot be divisible or cannot be divided evenly with a 4 and a 3. So as Johnny said, break the 4 into 3 and 1. 3 divided by 3 becomes a 1 here. So the numerator is going to become Do I need those 1s everywhere? No, I don't. I see Mike shaking his head. He's like, come on, we don't need 1s. Okay? We don't need these 1s here. So drop all the 1s. But please don't drop the cube root of 3, or the cube root around the W. A lot of people take the cube root of this one here on the left, okay, and then they forget the other part. So again, let's get rid of those 1s, please. Okay? And that's our final answer for this part. If you want to write it like this, just as a side note, here's a little side note. You can write it like this also. W over y as like a quotient, taking these out front and grouping them together. Okay? And then the cube root of w by itself. You can write it that way as well. And just so you know, because if you see this on like an SAT, you should know that those are the same things. Okay, those are interchangeable. Is that clear? Okay, please know that. All right, last example. The square root of 9w squared plus 9u squared. Now, why can I not start by breaking this into components? Again, why can I not start? They're addends. Addends cannot be separated like factors can. So that's the issue we have right away. It's very desirable to say 9w squared plus 9u squared under separate square roots. But clearly we can't do that. What can I do for this problem? What can I do? Factor out what?
9.
Good. Okay? Jules, next.
Separate them.
Good. And tell me, Jules, what do you think a common mistake would be at this point that some students might make, and not you, some other people might make? What's that?
I did 2 factor w squared plus
Yeah, it's very tempting to make this just w plus u, right? Just to say, well, you know what, there's a square root and there's a square, there's a square root and there's a square, let me just, cancel them, right? Seems like you want to do that. But these are addends. When there's addends, you can't distribute the square roots each. If this was w squared times u squared, sure, you can just drop them off. So this becomes 3, and you're done. You cannot go further. You want proof of that? Let me give you proof of that. Hold on, before you ask a question, Alejandro. You can't go any further, but let me give you proof. Okay, let's say we have square root of 2 squared plus 4 squared. Mike, what does that come out to be in the inside when you square both of those?
20.
Mike, what's the square root of 20 approximately? Between what numbers? Between what two integer values is the square root of 20?
4 and 5.
Yeah, so it's like 4 with a decimal, right? Okay, 4 point something. Agreed? Yes? No? Maybe so? Okay. Now, Erickson, if you were to do the incorrect way and take the square root of both, the square root of 2 squared becomes just what? If I were to write it like this, this is incorrect. You're not doing this. What does the square root of 2 squared become? And what's the square root of 4 squared become? What's 2 plus 4? Is 6 the same as 4 point something? Is it obvious now that if you separate the square root, you don't get the same answer here? Again, separating the square root is not valid. This is the value you should be getting. If you separate, you can clearly see you don't get anything near that value. Okay? That is not correct. Is that clear? We want to make sure we all get that part.
So for the one before, would it be 3 times, and then you write the cube side? Oh, wait.
It wasn't a cube root, it was a square root. It's all right, not a problem. Okay. How are we doing? Is this a lot to take in already? We're about halfway through. Go ahead, yeah. Sure. Like part D? Another example like part D? Yeah.
Many are everyone is twins, and I want us to wear like turban costume. I told that, and then he said no.
Spartans.
No, Spartans don't wear.
I'm not going to go out when it's like 30 degrees outside.
We'll get lots of.
This one. The subtraction indicates right away, well, something's wrong here. I can't do this. So as Katerina said, we should do something, right? What should we do? Factor. Johnny, what's the GCF here that can come out of 48 and 32?
6 or 12 or 16.
There it is, 16.
Alright,
Oops. Hold on. Put plus. Now, 16 square root is what, everybody? 4. So again, think of it like this. Okay? Now, yeah, Alejandro, I heard what you said just now, and that's a good point. It looked like it was going to be difference of squares, right? Let's say, hypothetically though, let's say you were able to factor it out. So the final answer for this problem is this, by the way. You can't go further, okay? But let's say the problem was an example where you had difference of squares. You still can't go further because they're different. They're not the same. And that's a point I want to make, and that's a good point that you made there. So let's say we have x squared minus y squared is difference of squares, right? But this becomes this, remember? Are those the same? Yeah, but I mean, like, is x minus y the same as x plus y? So this you can't reduce, actually. You would have to leave this like the way it is. So difference of squares doesn't really help us when it's under a square root here. Okay, you know what would help us? An example like this. You're going to see one of these in your homework. What can you factor that into?
X plus 5.
X plus 5.
X minus 5.
No? Yeah. It's this, really.
Square.
It's x plus 5, right? Peter, agreed? x plus 5, x plus 5. Well, then you can reduce this, because the square and the square root actually cancel here. Okay, it seems as if because there's addends you can't do it. But this, if you remember, is really this.
Oh, it's not.
It is. It's been for a little while.
That's how you told me earlier.
Okay? So again, the square root of 25 simplifies because it's 5 times 5. This is no different. The square root of x plus 5 quantity squared simplifies because it's x plus 5, and that's what the definition of a square root is. Remember how we defined a square root. It's the solution to this equation, where you have to find a number when multiplied by itself gives you that answer. Well, this is the number, or the quantity. This quantity, x plus 5, is multiplied by itself. So because you see it twice, you can reduce it. Okay? Tonight, what I want you to do for your homework,
Is this on Moodle?
it's going to be, but I'm going to probably...
Wait. You're not allowed to have a radical on
Where's
one,
that?
right?
We're going to talk about that today, though.
Okay,
See, that's what I didn't get into.
Yeah, there was questions on that.
If there was anything with the radical in the denominator and you have trouble with that, we're going to take a look at that today, and it's called rationalizing the denominator. Okay?
Okay, so there was another question.
Go ahead.
Yeah.
Just check. Next.
Which one with
2 radical 2.
Sorry? No, 3. No, yeah, 3.
3 radical 2?
Like the little 3, the baby 3.
Cube root. Cube root. I thought you said 2 root 2. You said cube root.
Cube root of 2
cube?
divided by cube root of 9. Didn't find it anywhere.
Yeah, okay. Sorry. So remember yesterday at the end of the period, I was like, let me look to see if there's any homework problems I want to exclude. And I looked through there real quick. This is one that I should have excluded because we didn't get to the denominator thing. We're going to do that today. So if you struggle with this problem, just leave it for now. It's not a problem at all. Okay? Go ahead. Others?
Yes. Then it's,
We're going to go over that today, though.
oh, okay. Cube root of 6y minus 4. I mean, to negative 4.
Five.
Oh, yeah. Times cube root of 9y squared.
9y squared?
I got it.
Like that?
Yeah.
Okay. So we start by remembering. Remember the first law that we talked about yesterday. Radical AB equals radical A times radical B. So we can multiply the radicands at this point. And you should always start by doing that. So 6 times 9. Everybody? Or somebody?
54.
Thank you.
54.
Y to the negative 4 times y to the positive 2. Jules.
Y squared over y4. Y negative.
Okay. And I'm going to write that for now as y to the negative 2. Very good, Jules. So Jules started by putting the y to the negative 4 in the denominator. Okay? So if I add the exponents, that's what I end up getting down here. Now, at this point in time, what you're going to see is what Jules said makes a little more sense to write it that way. Okay? And that's probably what you have at this point. Okay? Now, can 2 be divided by 3 if I look at the exponent here? See this 2 right here? And see this 3 right here? This 2 cannot be divided by this 3. So you can't really do anything with this y squared. There's nothing you can do with it. So you can actually, in the end, we're going to talk about rationalizing the denominator, but for now, we're going to leave it there. Once we talk about today, we'll go into that. But look at the numerator, 54. What's a perfect cube that goes into 54? Perfect cube that goes into 54. 27. What's 27 times 2? 54. So write this as the cube root of 27 times 2 over the cube root of y squared. Now, the cube root of y squared, again, just for today, or just for last night's homework purposes, we're going to leave alone. We're not going to do much with it.
Why is the y squared at the bottom? Shouldn't it be y to the negative 4? So it should be back at the bottom.
Yes, but then you would have y to the negative 4 on the bottom and y to the positive 2 in the top, which would reduce, right? So what Alejandro's saying is this. If you went from this line, if you went from this line over here and wrote it like this, right? That's what you're saying? Okay, over here? That's what you're talking about? Sure, that's correct. But again, what's going to happen is this is going to cancel with two of these, leaving this as y squared. That's this denominator right here now. The numerator, the 27, can be reduced. What's the cube root of 27? 3. So put a 3 out front. Then you write the cube root of 2, because that's left behind, over the cube root of y squared. Now today, we're going to talk about how to get rid of that denominator. That's going to be our first step for today. So you would continue this problem. So for now, leave it like ... and you can finish it up tonight.
I did something weird in that, because that's not the answer to the book gives you in the back. I got the answer to the book gives you in the back. I don't know how to do it.
What was your method? Maybe you can lead us into today's lesson.
I got 3 and cube root and then that is 2y. And then divide by y.
That's correct, but how did you get that was my question. Now, what did you get?
Well, I did multiply times whatever times each other. Because that's something you I did 6. And then I just did factor them out. And I got cube root. I just say 2 is 3 times 3 times 3. And then I multiplied those. It's longer, but it's...
Well, I mean, at this point in time, I'm saying, what would you do? Because this is kind of what we're going to do today with the lesson. How would you make this look better?
Don't you multiply it times the reciprocal or something like that?
Close. You multiply this by something to give you a perfect cube in the denominator. So, here's what I want you to think about. If I wanted y cubed in the denominator, what do I need to multiply the denominator by? Yeah, cube root of y, but another y, right? So if I go like this, watch what happens. But I need to, if I multiply by the bottom, I have to multiply the top. Remember, if you're going to multiply by a fraction, it's got to be 1. And 1 is really this. This is what we're going to learn today, and we'll go into more detail. But this is what you would end up doing. Now, if you look at the numerator would become 3 cube root of 2y, because this 2 and this y now are together. See that? And when you put this y squared with this y together, what does this become? Yeah, and then the cube root of y to the third cancel each other out, leaving behind a y in the denominator. So again, this is really cube root of y to the third, but then this will reduce to just y in the denominator. So you're going to end up with 3 cube root of 2y over y. But again, I'm jumping the gun, I'm just going in the answer, but we'll go over how to do this today. That's what we're going to start with.
How? I just did 3 cube 2y squared over y cubed y. And then I cancel out the y's.
That's what I did.
That works.
I don't know if that's
Does that work?
It works, but it's like you're putting an extra y in there and then canceling it. So you're kind of, like, in a sense, doing one of these, you know? You add something in and then you get rid of it later. So it's more work, that's all. That'll work, but it's sometimes easier just to say, what can I multiply to give me a perfect cube or a perfect square or a perfect fourth or whatever it is. Okay? But that definitely works. Other questions on the homework before we go into today's? Jules?
Square root of 6 times squared. Like that's in parentheses and then it's squared.
The whole thing is squared? So that's the question? Okay. What do I do here? Summer?
Usually like distribute the square.
Exactly. It's the same as your laws of exponents. Just distribute the square. Okay? Make sense? So again, remember the law of exponent. This is this. Correct? You distribute the c to both terms. Same thing. Okay, you square the 3. That'll give you 9. You square the root 6 to give you 6. 9 times 6 is 54. Other questions? Good questions, guys. Katerina.
16.
Okay.
It was like the square root of 35 times the square root of 21.
Yeah.
And I got the square root of 735.
And that's a mess, right?
Yeah.
Okay. Good point to notice here. She said, well, I do this and I'm going to get this crazy answer. There's a little trick for this problem. Did anybody pick up on it?
I think I did. I put the square root of 7 times 5, and then the square root of 3 times 7.
Yeah, that helps you. Because now see the 7, 7? What does that become? Square root of 49, which is just... So it's going to become 7 root 15. Because you're going to get, again, take the 7 and 7 together, take this 7, and this 7 make it 49. In your mind, that becomes 7. 5 and 3 becomes 15, and your answer is 7 root 15. Had you not done that, it's going to be a messy problem, right? What was the number you had?
I don't even remember. I just did it in the calculator.
Okay.
It's like, yeah.
And it's tough to know that whatever that answer is, so you're going to get an answer if you multiply these two. 735. And then 735 breaks into 49 times 15, but does anybody happen to know that off the top of their head? No. So you have to sit there and try it in the calculator. So to avoid that, you can try to break them down. Even though these are not perfect squares, if you see the same number and it's not a perfect square, you can then use that number. Okay? Look for that correlation. Okay? Look for that. Yes. Other questions? Other questions? Alejandro. Louder.
Cube root of 32 to the negative 3.
32y to the negative 3?
A.
A.
The negative 3 and b to the 4th, all under the round. Do you take, you just put down the a?
Mm-hmm. This is where our laws of exponents come into play, right? Negative exponent, Johnny. What do we do when we have a negative exponent always? Yeah, you move it to the opposite location. So, Pete, if the negative exponent was in the bottom, what would you do with it?
Move it up.
Yeah, move it up to the top. But now it's in the top, so we move it to the bottom. So, Jules, tell me, what can I do with the rest of this problem now?
32 would be 8 times 4.
Good.
B would be b cubed times b, and then over a cubed.
See what I'm doing? I'm breaking it up and also just distributing that cube root to everything. So the 8 becomes 2. The b cubed becomes b. This is what I do in my mind. You don't have to write it and cross it off, but this is what you should be doing. A cubed, cube root becomes a. Everybody agree with me so far? What's left is just 4 and b. So just go like this. Put it on the side. Or you can put that in the numerator. So that's fine, or this. Okay? Either answer is acceptable. And again, we talked about this yesterday. Either answer should be understood, because a multiple choice test, you have to think about which one is right. They're both right here. You're not going to get both of these choices, but if you get this as your answer, and that's not there, and this is the multiple choice, you need to select that choice, and so forth and so on.
Under radicals, you can still subtract
Exponents?
in English right now.
Exponents?
No, the letter, what's the word in English?
Variable?
Yeah, the variable. You can only subtract, you can still do the same thing, right? And you can do if it didn't have a radical.
Yeah, same rules apply for exponents and variables under the radical as if they do outside. Yep. Okay. Alright, so this is going to lead us into today's lesson. Okay, and it's continuation. So we're still on technically section 6.2. We'll see how far we get. I want to get through 6.3 also. 6.3 is actually quite easy, and you'll see that today. 6.2, the end of it is rationalizing, so we're going to talk about. Okay, you don't have to write all this down. Okay, you don't have to write all this down. Let's just read it together first. So write the topic down, though. Rationalizing the denominator. So, can I get somebody to read the next process from that point? Summer, go for it.
The next process, although less important since the introduction of the calculator, is a technique that will be used in calculus class to help simplify complicated expressions.
So, again, this technique, and this is going to sound like I'm really old, even though I'm not old. This technique was widely used when I was in high school. Okay? It's called rationalizing the denominator. Now, it's extremely useful, especially when you get to calculus, because you're going to get these expressions that are very complex, and you're going to have to simplify them. And this technique is going to help you do that. Okay? Now, it's not really, honestly, in my opinion, very useful if you're not in calculus. We're going to learn it either way. Okay? We're going to learn either way, because hopefully most people in here, everybody, will go on to take calculus. Okay? So it is going to be a useful technique to think about. Alright, the next part to read. Manny, can you read from the main idea? Sorry, Mahanor, the main idea?
The main idea is simply to create a perfect square, cube, or other power of the denominator, whichever is needed, in order to simplify the denominator to an expression without a radical.
Okay. And that's exactly what we said earlier. We were looking for that perfect cube. Let's start with example A, which is a little easier, where we're only looking for a perfect square. So, I start by looking at A, and I say, okay, well, it's really just radical 7 over radical 3. Okay? Now, the radical 7 up top, I cannot reduce. The radical 3 in the bottom, I cannot reduce. So, there's nothing I can do as of right now. John, tell me, what is something I can multiply 3 by to give me something that makes it a perfect square? 3 times what number will give me a perfect square? Any perfect square. Yeah, 3. Simple as that, right? Because what's 3 times 3, everybody? 9. So watch what happens. Let's multiply. So if we're going to multiply the bottom by radical 3, what do I have to do to the top? Same thing. So let's start by doing that. What does the top become, Erickson? And the bottom? So as a result, your final answer? What does root 9 become?
3.
And that's it. Okay? Again, that's all rationalizing is. It gets more complicated when we get to variables and cube roots and square and fourth roots and so forth. But that's the gist of it. Whenever you have a perfect, when you ever have a square root and it's all numerical values, no variables, just multiply by the denominator over itself. Is that clear? It's a little trick for the square root. It always works. For other ones, it's not always going to work. When there's a variable, when it's not a square root, etc., etc. But here, whenever there's a numerical value and it's just a square root, just take whatever this is right here and multiply it by itself over itself. Okay, and it will simplify. Questions on this so far? Can radical in fractions? No. So like 21 over 3 cannot be, it's like not like terms. This is what I think about. Imagine this is like y, this is y, and this is x. They don't reduce, right? Y and x. These are two different things. You can only simplify things on the inside and on the outside of the radical. Again, this is considered to be, this 3 here is like it's on the outside of a radical. There's really, what's next to this really? There's really a radical 1 next to it, even though you don't see it, because what's the square root of 1? This is 1, right? So, in this sense, you really have 21 over 1. So you could simplify 21 over 1, but that's still just 21. So there's no need for that. But the 3 is really technically on the outside of the square root. Okay, on the outside. All right. Let's take a look at part B. How would I start by writing this? Write it as what? Pete.
2 roots become so
Good. So what do you got up top, Pete?
3.
And the bottom?
A.
Root A. Good. Now, Pete, from the last example, let's utilize what we learned. We said we wanted to get a perfect square, so what can we multiply A by to make it squared? Yeah, very good. So let's multiply by root A over root A. Numerator becomes root 3A. Denominator becomes root A squared. But we clearly know the denominator now becomes what, Manny? When I have the square root of A squared. A, God bless you. Just A, very good, Manny. God bless you. Okay? And that's your final answer for this one. So we see how with the square root it's quite simple. Is everybody, right? Would you agree it's not that difficult with the square root? Okay? It's no more difficult with a cube root, with a fourth root, with a fifth root. It's just different. It's just different. That's it. All right? So let's look at part C. Fifth root of C. Sure, absolutely. I'm going to rewrite it. Fifth root of C over fifth root of C squared. Fifth root of C over the fifth root of C squared. And yeah, it looks like it's complicated at first, but what kind of a root is this? A difficult one?
Oh, it's a fifth root.
It's a fifth root. So you want a perfect fifth. Like a square root, you wanted a perfect square. A cube root, you want a perfect cube. A fourth root, you want a perfect fourth. So what can I multiply, Summer, in the bottom?
Radical root as 5 squared. Sorry, c third.
Good. So let's say it together. The fifth root of c cubed. Okay? Again, the way you always say these, just look at this number and say fifth, and the radical means root, fifth root of c cubed. Okay? So let's multiply top and bottom. Okay, numerator. Nick, what do I get in the numerator here?
Doesn't it, do they cancel out?
Well, just for now, add the exponents together and see what you get, and then we'll talk about canceling. Okay, so we have fifth root of c times the fifth root of c cubed. Keep going.
Fifth root of c over times fifth root of c cubed, c to the fourth.
Good. So fifth root of c to the fourth, which can't be reduced, because remember, 4 cannot be divided by 5 evenly, so that's not going to help us. It's going to stay there. But the denominator now becomes, yeah, so fifth root of c to the fifth, which really is just c. And you leave it like that. Okay? That's as far as we can go for this problem. Katarina.
Why is it so important not to have a radical?
Did you see I put to read something for your homework? I said read page, I think it was 266. It goes into the whole explanation of where that comes from and why. The idea was that it is much more difficult to find 2 square roots without a calculator. Let me show you an example. Before calculators were invented, we used what are called root tables. Same thing with like trig functions. Sine, cosine, tangent on the calculator is easy, but I used to use trig tables actually. You had these tables of values, they were all decimals, and you would run up and down the rows to interpolate the data. So, here's an example for you. Imagine if I asked you to figure out what the square root of 8 was over the square root of 3. Okay? That means you have to do 2 separate problems, old school wise. In a calculator, yeah, that's one problem. But when you used to use tables, you would have to do the square root of 8 and the square root of 3 separately and then divide those decimals, which is messy. But if you rationalize it, you only end up with 1 square root up top. And what that means, take a look at it. Multiply by root 3 over root 3, you're going to get root 24 over 3. Root 24 can be broken into 4 and 6. 4 becomes just 2. So in the end, take a look. If I simplify this from the beginning, which is boxed in, to the end, which is circled, earlier, God bless you, I would have had to do 2 separate problems in a sense. Now I can go to my root table, even though you're not going to do that now because you have a calculator, and just figure out the square root of 6 as a decimal, and then multiply by 2/3. Okay? They were invented, I'm not that old. They were invented, but like, I would say like maybe 10 years prior to me going to high school, there were no calculators as far as handheld calculators. There were like big computers that used calculators, but there weren't, yeah, true story. But again,
So weird.
I know. But when I was in school, they had them. But for your purposes, yes, I agree with you. Right now, honestly, and I'll tell you the truth, and Mr. Linus will tell you the same thing. It's pointless to know how to do this just for this class. It really is. But this is a technique we're learning so that when you get to calculus, you don't have to relearn it. Okay? It's a thing like learn it now so when you get to calculus, you can use it then, and it's even more difficult in calculus. You do stuff that's a little bit trickier than this, but you're still using the rationalization technique. It's still there. Okay? This also leads us into, and we're not going to do it today, but we're going to do it soon, imaginary denominators. Complex, binomial, imaginary denominators. And that's when you have I in the denominator. And we're going to use this term called a complex conjugate, which comes from this technique. So it's going to be used in imaginary numbers also. But as far as when it's going to help you right now, it's really not. It's just learn the practice, learn to do it. But there is a reason. I wouldn't just make you do something for no reason. Okay? But that's a very good question. You should always question stuff like that. Right? Why are you doing something? It's a good question to ask. All right. Should we do another practice one of this before we go on? One more? Yeah? Maybe a little more complex? Okay. Say again? The technique? Yeah, I mean, there's some brilliant mathematicians that lived. I know the, who was it? The Mayans, I think? The Mayans invented a technique to approximate square roots, and that's where we actually get our tables from. And then calculators use another technique now, and it's a series expansion to get numbers. And thank you, Erickson. And and that was like, I mean, we're talking thousands of years ago that they invented these techniques. So there were definitely some really smart people, much smarter than.
Except they couldn't understand the wheel.
Except they couldn't understand the wheel.
Why aren't there any smart people like that anymore?
Oh, there are.
Math people?
Absolutely. The thing is this. So much stuff has been invented and discovered already that it's getting more and more difficult to come up with these new theories or these new ideas. People build upon old stuff. So like Einstein's theory of relativity. It's not like, it didn't stop there. There are people in physics that are constantly making further breakthroughs. They're not as big as the breakthrough as relativity was, so maybe they're not published as well. Or maybe because, no offense, you're in high school, you don't see these publications. I know for me, when I was in college, I used to read the Journal of Engineering. And it's where all people publish all their new research. And there is such crazy stuff going on there. I mean, amazing things. I mean, think about it as something as like a touch screen. We take it for granted that I could just touch the screen and write, and that I could wirelessly send a signal. Those breakthroughs are amazing if you think about it. They're almost as unbelievable as the stuff that people did thousands of years ago, but it's a new phase, it's a new idea or a new era. So we might not see that because so many people are doing other things. I saw this the other day, this video, and maybe I'll post it on Newsfeed. See, I love teaching physics. I love math too, don't get me wrong. But I love physics because it's so application-based. That's the reason I like it even more. And I love math, and I'm definitely teaching this class again next year because I like it. But even on their news feed online, I post videos and articles to this crazy stuff. The other day, I found this new tablet. It's amazing. The screen is malleable. It morphs. So you know how if I wanted to bring up a keyboard on here right now, you hit that little button, the keyboard pops up, and I can type? The new one they just came out with, the screen itself actually shapes into letters on the keyboard. You know how when you're on a laptop you can feel the letters? The screen is this material that morphs based on an electrical signal put into it, and you can feel the keyboard on the screen. It's out of this world amazing. I saw it the other day, and I put it on the physics website. Such crazy stuff. Another one was this particle that was levitating and going around a track using different polarities, and it was kept on the track. And it's called a maglev. And that's where the train there's a train in Japan that they're building that runs on a maglev. They're magnets that let it hover above the ground, which makes it almost frictionless, which allows it to go up to speeds of 200 miles per hour, such crazy speeds. So there are a lot of things going on. It's just nothing there's no, string theory is a big thing right now. It's huge.
What is?
String theory? Sheldon? Just Google it. I'm not going to go into string theory now, but it's the idea that particles act as strings that vibrate at different frequencies. And based on the frequency, it indicates what kind of a particle it is. So a helium atom would be vibrating at a different frequency as a hydrogen atom, and so forth and so on. So it's a really interesting theory. Nothing has really been proven solid yet, but these are theories that are out there. If you want an author, if you're interested in this stuff, Brian Greene wrote a good book that's very user-friendly. User-friendly, it's readable. Some of these books that people read are just crazy. I don't even know what they're saying. But Brian Greene wrote a book called The Elegant Universe. There's also a movie on it, so if you want to watch the movie's really cool too. You know what Nova series is?
Yeah.
It's a Nova series. It's a 3-part Nova series. I have it if you want. If you want to borrow it, just bring in the flash drive. Bring in a flash drive. I can put it on there for you if you want to watch it. It's 3 hours. It's an hour each section. But the book is much longer. So if you don't have the time for the book and you want to just watch something cool, he talks about string theory and quantum mechanics. Anyway, not to but there is a lot of stuff going on. Let's do another example though. Another example of rationalization. So let's say we have the cube root of, and we're going to make it a fraction. I want to make it a good problem. Hold on.
Difficult.
Yeah.
He loves doing this to us. He really does.
Okay? Sorry, that is supposed to be a normal 3. It looks like it's like hovering, right? Yeah. So cube root of the quantity 3y to the 4th x to the 7th over the quantity 48y to the 6th x to the 2nd. Okay? I want to go through this together, one step at a time. Who can lead me through this process? Lead me, please.
First, start by making them 2 separate problems.
Yeah, you can make them 2 separate problems. Now, to make it easier, Summer, do you see that there's anything in the top and the bottom that are similar?
Very.
Yeah, so reduce for me first.
Okay, you can reduce the y top to like nothing, right?
Good, and the bottom becomes?
Y squared.
Good.
And then you can reduce the y squared in the bottom.
X squared.
Yeah, sorry, x squared.
And the top becomes?
X fifth.
Good. That's right. And what about 3 and 48? What do they differ by? What factor? 16. So that would become 1 over 16. So I'm just going to put a 16 down here. Because I know that 48 and 3 is divisible by 16. I remember, watch. 48 is really 16 times 3. So you end up with, if I look at this and rewrite it like this, see the 3's cancel? Leaving behind a 1 up top over 16 in the bottom. Okay? It's the same thing as if you had 48 over 3, just the reciprocal. All right. So we've got the cube root of x to the 5th over 16y squared. Denominator we clearly can't have. The numerator can be simplified further. So let's go through this process. Who wants to do this next part here? Erickson.
Multiply 16y squared because that's literally nothing.
Okay, now let's stop there because I want to point something out. That works for square roots, remember I said? But what kind of root is this? What kind of a root is this? Cube. So let's stop and think before we go any further. The numerator can be broken into what components where we have a perfect cube? What can I break x to the 5th into so that I have at least one perfect cube?
X to the square and x squared.
Okay, so let's start by doing that. Okay? Cube root of x to the 3rd times the cube root of x squared. It does, but we never see it. Now, if you want to, notice what I do with my root sometimes. See how I put a little close at the end of it? It indicates to me that the root ends there. Okay? Because sometimes it kind of drags over. So you might want to start closing your roots. That's good up top. Very good. The bottom, the y squared, we can't break up, right? Y squared is, we got to do something with the rationalization. But 16 can be broken up. What are some factors of 16, one of which is a perfect cube?
You can do 4y and 4y.
Okay, but those are perfect squares you're thinking of now. We want cubes.
I wanted to know if you multiplied the 16y squared by y, can you get 16y to the 3rd?
Yes, and we're going to do that in a second. Hold that thought. Break up the 16 first, though, Mike. 8 and 2. So let's write the bottom like this now. Okay? Summer, we're going to use what you said in a minute, okay? So we break up the 8 and the 2. Johnny, tell me, in the numerator and denominator, right away, what simplifies?
3x to x to the 3rd.
Cube root of x to the 3rd becomes?
X.
Good. And we're left with the cube root of x squared. In the denominator, what's the cube root of 8?
2.
Good. So here's where we're at now. We all agree so far? We're going one step at a time here. This is where we're at right now. Summer, back to your statement. Make it again, because it's correct now. It was correct before, but I would simplify everything I can first and then go through the process.
Okay, you could multiply the 3 radical y squared by y squared. Well, I mean radical y.
Okay, so we can multiply the top and bottom by the cube root of y. Right? Is that what you're saying? I think that's what you're saying. So multiply the cube root of y in the top and the bottom, which then makes the y squared, everybody, y cubed. Okay? It makes this y squared that you see right here y cubed when you put these two together. It also puts a y under here in the numerator, but that's fine. Not a problem at all. Okay? I want to also get rid of that 2 though. Everybody see that 2 down there? What can I multiply 2 by to give me a perfect cube? 4. What's 2 times 4? 8. That'll make the denominator a cube root of 8 now. So in addition, I'm going to move it over. Oops. Come on, there we go. In addition to the y, we want to multiply it also by 4. Okay? Now, just look at everything, please. Numerator becomes x squared y times 4, which we'll rewrite more simply in a minute. But I'm just writing it in the order you see it so it's clear. Again, where does that come from? X squared times y times 4. The denominator becomes 2 on the outside, cube root of. Now, watch what I'm going to do. This 2 times this 4 gives me an 8. This y squared times this y gives me y cubed. And now the denominator can easily be reduced. No. Come on. Now the denominator can easily be reduced. The numerator leave alone. And I'm going to write it in standard form, which is usually a numerical value, then the higher exponent, and then the lower exponent. Everybody see that? I put the 4 in the front there. Now in the denominator, Manny, what's the cube root of 8? 2. So we have a 2 on the outside, and now we have another 2 here. And then we have the cube root of y cubed. Pete, when I have the cube root of y cubed, what happens to those cubes? What does the cube root become when we take the cube root of y cubed?
Oh, y.
Just y. So my final answer is this, but instead of the 2's, let's just make that into a 4. And I'll actually rewrite it to make it easier. So your final answer might look like this. Okay? And I have a tendency to write my fractional parts on the outside as like a coefficient, x over 4y. You don't have to do that. You could have left it the way it looked. X cube root of 4x squared y over 4y. Yes? Hurry back. We have only a few minutes left, okay? Jules?
Maybe I just like multiply the 16 by 4 and then combine.
Absolutely. Absolutely. That works also. See the 16 we had in the beginning? And these are things you're going to pick up on. If that's easier, that works. And to be honest, now that I think about it, that probably would be easier. What Jules just said was this. Remember in the beginning of the problem, you had a cube root of 16 in the denominator? Look back at your problem, please. Everybody look down at your paper. You had the cube root of 16 in the denominator. And Jules said, well, what if we just multiply the denominator by 4? And that works, because that'll give you the cube root of 64, which is just 4. And that 4 does show up right here in the denominator. Okay? Questions on this?
Wait, just say that again. If you
Sure.
multiply it by 4, I don't understand that.
That's not a problem. What was the original I gave you?
It was x fifth over 6y squared. 16y squared.
Okay, so this is what we had at one point when we reduced it, right? Like that? So what Jules is saying is this. Instead of breaking the 16 into 8 and 2 and taking the cube out and then rationalizing, if you just multiply the denominator and numerator by 4, okay, if you just multiply it by 4, what ends up happening here is this becomes 64.
Oh, that's, you can do
And the
that.
cube root of 64 is 4, which would give you this number here. So watch, ready? Yeah, for sure.
Sorry.
Can you use a rainbow marker over there?
Yeah, really.
Use the what?
Rainbow.
It's not rainbow. It's just it's a palette of colors. Look,
What?
it lets you select colors.
What?
It's not a rainbow marker.
All of them.
You thought it was a rainbow marker the whole time?
Lady disappointed.
No, it's just like you can choose any color of the spectrum.
Make it turquoise.
Yeah.
Purple.
Are we getting original?
Guys, this
This is making us happy.
Better?
Oh, it's such a cute color.
So, this is what Jules said. If we did this, what would happen? The numerator would become 4x to the fifth. The denominator would become 64y squared. And 64, the cube root is just 4, which is where this 4 comes from, really. And see this 4 right here? This 4 shows up right here in the answer because it can't be reduced. So she was saying to simplify the numerical value easier, and we're not looking at the variables right now. The x to the fifth and y to the squared, you would do the way we did it. But to simplify the numerical value, you can multiply by the cube root of 4 over the cube root of 4 to give you this 64, which comes out, again, as this 4 right here. Okay?
Yeah, like the variables are not even out. That's how I can see.
Not a problem. Oops, didn't do that. All right, any questions on this? It's a lot. This is still only section 6.2. Okay? I know. Tomorrow we're going to be adding and subtracting rational expressions. Okay? Or rational expressions. Sorry, radical expressions. We're going to be adding and subtracting. Tonight what I'd like you to do is to finish up all the homework and make sure that any answer with a radical in the denominator now gets rationalized. So the homework that you did last night, remember how you couldn't really do some of them because they had radicals in the denominator? And I was like, finish them off? Tonight, please, make sure that you do so. Okay? Take a look at the homework tonight. Go through every problem again. Make sure they are all in simplest terms without a radical in the denominator. It is?
Okay, that's funny.
What do you do with activities?
What's that?
What do you do with activities?
Probably, oh guys, problem, so I want to check real quick. Let me just look. Only write down 6.2 for the time being. We're going to probably do 6.3 most of it tomorrow. Let me just quickly look to see if I want to make any alterations.
There you go.
And you can just not finish homework if you want.
Well, that's good.
Wait, so there's no. What is that?
Then Villanova beat Syracuse.
They did. Upset. 75-71 overtime. And Louisville. Only team unranked to ever be 2 ranked teams. Or 2 top 5 teams.
In a row.
In history. No, in history.
Who was it in history?
Yeah, ever.
Wasn't it like that?
The only unranked team to ever beat 2 teams that were in the top 5 in the season. Villanova this week was crazy. Alright, let me look. Hold on. I said 2 through 32 even. And then 39 through 66.
Basic facts.
Yeah, just do 6-2 tonight. Just do 6-2 tonight, please. Have a good day, guys.
No, it's not.